In order to solve the problem of heating coil, I have opened Ansys Workbench and I am going to take this steady state thermal and place it on project schematic. And now I am going to go to engineering data, go to engineering data sources, go to thermal materials library here, and in the thermal materials library I am going to select this tungsten. Once I select it and add it to my project, I am going to close the engineering data. Now I am going to right click on the geometry and I am going to say import, and I am going to browse, and I am going to select this particular heating coil and I am going to press open. Once I have imported the particular geometry, I am going to double click on the model cell in order to open Ansys mechanical and perform the further analysis. Here the mode of heat transfer is through radiation, so we need to give emissivity as well as this ambient temperature as an input. So once I have opened Ansys mechanical, the first and foremost thing I need to do is I need to go to this heating coil geometry and change the material from structural steel to tungsten. And once I've changed this particular material, right now what I'm going to do is I'm going to right click on the steady state thermal, say insert, go to this particular internal heat generation option, and I'm going to select the total body because internal heat generation is a property of the total body. I have selected the total body and I am going to press apply. Once I have selected the geometry, I need to give the magnitude of this internal heat generation, which is around 0.02 watts per mm cube. And once I have defined the internal heat generation, now I need to define the radiation boundary condition. As I have told you, radiation boundary condition is a surface property. So I am going to just right click, say insert, and go to the radiation, and in the radiation I need to select all the external surfaces. For that purpose, what I am going to do is I am going to select this particular surface first, and I am going to go to this, and I am going to set extend to limit, so that what happens, this particular surfaces along this total path will be selected. And once I have selected all the surfaces through this particular option, I am going to press apply. Once I have applied this particular radiation to the surfaces, I need to give the emissivity. Our emissivity value is 0.25, and I need to give the ambient temperature, which is around 30 degrees centigrade. Once I have given all the required conditions of internal heat generation and radiation, I am now going to right click on the solution and I am going to solve. And once the solution is solved, we are going to find out the temperature distribution and the heat flux inside this particular coil. Then once the problem is solved, I am going to right click, say insert, go to temperature, and I am also going to right click, say insert, go to thermal total heat flux, and I am going to right click and evaluate both of these results. And once I evaluate both of those results, right now I am going to select the temperature and I can view the temperature distribution inside the coil. And I am going to select the total heat flux and I can visualize the total heat flux present in the coil. Then coming to this, we can also see all these results in the form of vector arrows. So what happens if I put up vector display instead of contours being displayed, all the values are being displayed with this particular lines or arrows. So what happens, these arrows are going to show the magnitude as well as the direction. So the heat flux, the heat is coming out of this particular coil, so it is showing the direction that the heat is coming out of this top surface of this particular coil. You can also change the size of these arrows by just using this slider, and you can also change the display of the arrows by using these options and this particular option. Okay, so this is how you can use vector displays, and this is how we can simulate the radiation conditions using Ansys Workbench software. Then coming to the energy balance, as I have told you in assumptions, there should be energy balance when we are performing this steady state thermal analysis. So what is the amount of heat generation that we have applied to the coil? It is nothing but 0.02 watts per mm cube. Then what is the volume of the total coil? You can just go here to the geometry, and in the geometry you can go for the properties and you can see the volume. It is nothing but 15,978 mm cube. So what happens, 15,978 into 0.02 will yield you around 324 or say 320.5 watts of energy. So for that purpose, what I am going to do is I'm going to right click, say insert, go to the probe tool, and you can put up the reaction probe. And once you put up the reaction probe, you need to select the boundary condition. So here the radiation is the boundary condition that I have selected, and I am going to just evaluate this particular result. And once I evaluate the result, see here the value is equivalent to minus 324.88 watts, which is somewhat very near to our analytical calculation. So what is happening, as we are performing a steady state thermal analysis, the energy balance is there. So this is how we can also confirm that our analysis is somewhat good. Then in the next lecture, I am going to show you how to perform thermal analysis on a solenoid, where the mode of heat transfer will be a combined mode, where we have a convection as well as conduction mode of heat transfer in that particular problem.